subset of R. We say that S is disconnected. S is disconnected. Connected. If what is disconnected? If it is possible to find. If it is possible, it is possible to find what? To find a pair of open sets. A pair of open sets. Pair of open set. We call it U and V. U and V. U and V. Also of R. It is a set of R. Correct. Such that you see U actually and intersection S the V is disjoint, is empty set. First of all, it should be empty set. The intersection is empty set, and the U to with S non-empty set U V with S also non-empty set. V intersection S is non-empty set. And actually, you see that the third one, the U intersection with S and V intersection of S is empty set. Actually, I denoted by this. Okay, U and V disjoint set, and with S non-empty intersection exists. And S, the first definition, S can be written as U intersection S union V intersection S. Okay, this is the definition 1. Here, just I will put the definition 2 because usually definition 2 is also very often used. Same as stated, let S be the subset of R. Okay, definition. And S is open set. S is called. Now here, look. It is not said S is open. Okay, it's just it is said S is disconnected. But in the second definition, open set S. Open set. Here I can just say let S be open set. Let S be open set. Okay, let S be open set. So S is called disconnected. S is called disconnected. Is called disconnected if there are two open sets. If there, I can say there exist two open sets. Two open sets. If there are two open sets, exist two open sets, non-empty, U and V of R, non-empty also, non-empty, sets U and V, non-empty sets of R, such that, now please pay attention, U intersection V is empty set, it is disconnected set. Okay, it is disconnected set, and S is equal to U union. This is U union. So there is a little difference in this two. You see, in this definition, please pay attention. S can be written of the union of two sets, but the intersection of U and S and V and S, okay, can be written on the union, but not just U union V. Intersection with S, V intersection with S, and union. Okay, usually this one is more comfortable to identify, to find the two sets. Okay, two sets. But in both cases, do we say that U and V are open set? The first, to find open sets, U and V, and in the second, two open disconnected, if the two open set. You see, both of them are open set. Okay, in the definition, the disconnected set is given with the open set, because later on you will see it can be given by the closed set as well. Closed set, intersection of two closed sets. So by these two definition, we can actually arrange, or we can find. So this one I put it here because I need the space. So U intersection V is empty set, and U intersection S non-empty, and V intersection S also non-empty. So then S, but then S can be written as union of U intersection S, union V intersection S. Okay, so these two definitions, please. In both cases, U and V are open sets. Disjoint open sets. Disjoint. This one says disjoint open set. If possible to find two disjoint open sets such that S can be written as a union of two sets, then it's called disconnected. Now for the connected set, if set is not disconnected, it's called connected set. Okay, so that's the definition. Now, good example is given here in example one. Actually, I will give the different types of. First, the P sets is given as a set of X from R. Sets R. X less than or equal to 1, and X not equal to 0. Look, if X from R, then this set actually can be, if I divide into 2 the interval, it can be written like this. So this is on the left side, I have -1 up to 0, 0 not included, and 0 to 1. Actually, this T is equivalent with this two of the half open sets of two open sets. Okay, now look, if I apply the first definition for this example, how to define or how to find the U and V must be open set, and disjoint open set. So now for this case, I will write like this. It is a set of X from R such that X is less than, you see, 0, less than 0. Or I can say it is minus infinity up to 0. And similarly, V, I can construct V such a way from R such that X strictly greater than 0 or strictly greater than 0. Or this one means from 0 to infinity. You see, I'm constructing two sets, open sets. And we can check U intersection V is empty set. There is no intersection. This one not included 0. This one also not included 0, empty set. Right? Intersection U with S with T, intersection with T. Look, what is it with the T? U and with the T. Please pay attention. Intersection with this. You see, up to 0. Huh? Intersection comes from -1, 0. 0 here or not included, also here not included. So this is the intersection, non-empty. It is non-empty. V intersection T is from 0, this one to infinity, this is 1. So 0 and 1. Now, S, in my case, T, can be written as U intersection T union V intersection T. Okay, now look, U intersection T is -1, 0. -1, 0. Union 0, 1. 1 is included. Oh, Alhamdulillah. Yeah, they told me that there is a test. Okay, now you see, I was able to find two open sets, such that the T can be written as a union of intersection with intersection of two sets. Okay, so you see this one and this one is the same. Now, if I use for the same problem the second definition, what we can do? Okay, what we can do. So here also it is called disconnected if there exists two open sets, non-empty open sets, U and V of R such that intersection is empty, it is disjoint. So now here, look, I can take U as all the point of X such that X varies from -2, you see, and 0. Yes, in other words, I can say like this. Such X, such that X varies -2, 0. Okay. I think that way is better because this is interval. I will write as an interval. -2 X 0 and V. I will choose all the X such that from 0 X to 2. Okay. Now I am there is a difference. Look, yeah, this one is infinite, unbounded set. Yeah, I'm choosing the bounded set. You see, bounded set from below, from the up, it is bounded set. But the intersection of U with V is empty set. Yeah, you see here, I should choose U and V such a way that it should be. Now here there is a problem. If I say U is an open set, you see, by this definition, I am able to write T as this form. This is correct. Now, if I say U and V, okay, U and V is not, this is minus to 0, and this is 0 to 2. No, cannot write as a union of 2. So if I put here minus 1 to 0, and from 0 to 1, from 0 to 1, in that case, you see, I should put like this, minus 1, U and V, I have to choose with including minus 1. Then T is written as U union V. Then it can. But here you see that is called disconnected. Let S be the open sets. S is called disconnected if two open sets, not empty open sets. Okay, so in the case definition 2, you see U and V of course there are two open sets. I cannot apply for this example this definition. The second definition, I am not able to apply. Do you understand why? Because U and V not open. It is not open. And if I choose like this, you see the first part, this is the second part, then they are disjoint, and U and V gives the T. Then it is okay. But you see, second definition is not applicable for this example because this one not open. Okay, so please pay attention. So U and V not open here, not open. If not open, yes, we can use this definition. If because definition says it must be open. If there are two open set, non-empty, U and V of R such that intersection is empty and S equal to U union V. In other words, we should able to divide the interval into 2 or 3 and so on intervals. Okay, so in other words, from the interval, if we subtract some points, that point that type of set is disconnected set. Generally, you can see, you see, they are not connected. So 1 point out. Okay, now I do change, do little change. This T, I will give like this. It is a set of X from Q, such that the absolute value of X is less than 1 and X not equal to 0. What we can see, what this, you see here, not R, now Q. Q is the rational number set. If rational number set, this one not equal to this interval. Please pay attention. This is not this interval, minus 1, 0, 0, 2, 1. It is not equal. Okay, because this interval includes all the rational and irrational points. All the rational and irrational points. You see, here, yes, they are equal. Here, not equal. Okay, now for the rational numbers set, we have to be very careful because rational number set is totally disconnected. There is disconnected and there is a totally disconnected. Later on, we will discuss. Okay, so that's why you see for this case, we can find generally infinitely open sets, infinitely many open sets containing, you see, the rational number and irrational number. I mean, the small interval, the interval we can construct open interval. That the T can be used as like this, you know, T can be used as a union of, for example, VI by from 1 to infinity. VI. You see, we can write infinitely many open sets, the union of the open sets, where Vi, and intersection Vj is empty set. Disjoint. We can construct infinitely many. So that's why for the Q, we have the special terminology, totally disconnected set. Okay? So now in general, the principle of the disconnected set is clear. Connected set is just opposite. If set is not disconnected, then it is open. Okay? Now there is here the second example. Okay, is disconnected. You see, for the first set, it is half open, half open, the union of the half closed sets, see, this is half closed. Do you remember? As an interesting example, if I take this T, and what I'm going to say, previously, what we learned. Okay, previously we have learned it, if set of T is a set of X such that X belong to the R, so which is minus infinity to plus infinity, right? Minus infinity. So this set is open. On the other hand, T complement is empty set, and empty set is also open. According to the definition, if TC is open, then this is closed. See, it looks like contradiction, but there is no contradiction. So T is open set, and at the same time closed set. Empty set is also open set, at the same time it is a closed set. Okay. Now here there is later on one interesting point. Say that there are some more sets which is open and at the same time is closed. Except these two sets, there are some more. But only thing that so far I couldn't construct another new sets which is open and closed. Okay. So on the other hand, for the closed set, and if you remember, that for any if any A or any S is written as A union A prime is set of accumulation points. This is closed set, always closed set. Okay, A union A prime, or S A A union boundary of A, BD of A is also closed set. We have looked. So for the closed set, we have few type of formulas, and currently we have the two sets which is open at the same time closed. Okay. Now we can look the next. Can you go to now? See, for the 3-2 can be used two definitions. Okay, both definition can be used to solve the second one. Okay, example 2 also, please. Okay. Please, I don't want to write because it is already open set. The given set is open set. So therefore, we can find two sets, U and V, open sets, such that the T can be written as union of two sets. Okay. So generally, if given set is open, then we can use the second definition as well. But if it is not open, given set, not open set, half open set, for example, or closed set, then this the definition 1 is better. Actually, definition 1 here, U and V, you can construct such a way under this condition. Under this condition, you can construct such a way that always S can be written as union of these two sets. Okay, that's why this one can be applied. You see, half open interval also can apply. So definition 1 is more proper. Okay, the second definition is only for open sets. Okay, now this example I will finish and go to the next. There is a theorem. Okay, so now this is U intersection V and MT. So this is the second definition. And okay, so please pay attention here. So this union should be equal to S. Next definition. Look again. Definition says that S be the non-empty subset of R is subset H of S is said to be open in S if there exists open set U in R such that H can be written as union intersection of U and S. This is another type of open sets. Do you remember the first main open set definition? Do you remember? One of you. When we say that set S is open, huh? Okay, any set S is open if if every element of X in S with epsilon neighborhood belong to S. In other words, every point in S is an interior point. Okay, this one we call it interior point. If every point is an interior point, then set S is called open set. Okay, open set. So we know the boundary point and so on. Actually, in the exam, many students make mistake in the accumulation point, interior point. I have given very clear picture and good example. Still you confuse in the exam. So actually when exam comes, your mind should change totally in different space. Okay? Okay. So what I'm going to say, so here this definition 3 is another alternative definition of the open set. Actually, there is no clear example, and I also wasn't able to construct the example to this definition because it is said that a subset. You see, H is a subset of S. S is a non-empty subset of R. Is said to be open if there exists open set. So H can be written as an intersection of H. You see, H is a subset of S. S is a subset of R. So now the H can, if there exists open set, and there exists open set U in R. If there exists two open set U in R, of course should be in R, such that H can be written as U and intersection S. For example, what kind of example I can say to be clear to this picture, to this definition. So let S, okay, in the case, I can say S, let's say interval 0, 1 from R. Okay. Now, S, the H is a subset of S. You see, subset of S. It is subset, not a proper subset. H of S is the subset. H of S is said to be open if there exists U, the open set U, such that U and intersection S. So now I can say U is a set of X such from R such that X, okay, X so I can say X less than, for example, the open set less than 1. Okay, if I took like this, can I H is the intersection of U intersection with S? What about this? Okay, you see this one like this. Intersection of U is an open set. Intersection with S is a closed set. So you can see I cannot construct U such a way. Which way I can construct? If I take like this, look like this, then I can construct U with this way. Then this one is open set. Now you see, one is not included here. S is not included 0. So then this one is open set. Actually, this definition is also not very complete definition. So you see, the S should be some kind of half open interval. Then we can construct. If it is fully closed, and here it is not say 2 sets, only one open set. There exists one open set such that the H can be written as the intersection of 2 sets. Okay, so this is another definition. Actually, this definition very difficult to use. Next, subset S of R is disconnected if S can be represented as a union of 2 non-empty disjoint open sets of S. Exactly this definition. Okay. So it can be represented as a union of 2 non-empty, they are non-empty, but the disjoint. So union of 2 non-empty disjoint open sets of S. Okay, so same, nothing. Now, what about this theorem? Actually, this theorem surprised me because in the proof you will see these 3 definitions, 3 what we call it equivalent statement. 3 statements are equivalent. X now here S is changed to the X with the subset of R. The following are equivalent. X is disconnected. That one is equivalent. So X can be represented as a union of non-empty disjoint. You see, disjoint, not open. So it's a subset of X. Closed subsets of X. In the first definition, look, S is disconnected if it is possible to find a pair of open sets U and V. Actually, disjoint. I can say disjoint pair of open sets such that this non-empty intersection and S can be written as a union of 2 sets. So there are some 1 hour. If people come, actually we shouldn't give admission. You are very kind, huh? Supporter. Okay, so can you now bring the the proof of this theorem. So, yes, the definition no need. But for formulation of the theorem is needed. Okay. I think later on okay. Now you see these three definition, three equivalent statement. If X is disconnected, so it is equivalent to the second one. X can be represented as a union of two non-empty disjoint closed subsets of X. Okay. Now, what they say in the proof. So from A can be reached to the B, and from the B can be reached, or from B can derive the C, and from C can derive A. Usually that one is correct. This the proof. So we will prove from A to B. So now here we just use the X. Let X be what disconnected set? B disconnected set. Disconnected set. Disconnected set. Okay. Let X be the disconnected set. According to the definition, if it is disconnected set, then what the second definition? X can be written as union T. Second definition, S union T, where S and T are disjoint. S and T are disjoint, non-empty. Disjoint, non-empty set. Okay. Now look at interesting point. So B the X is the disconnected set, and it can be written. And here, look, S and T, according to the definition, both open set. According to the definition, S and T are the open set, and union can be written as X. Definition 2. Okay, I am using definition 2, and they are disjoint. Now, here the interesting point, S can be written as X minus T, and T can be written as X minus S. Look, S is just disconnected set. Now, I am subtracting from disconnected set one part of the T, open sets. Okay. Now, interesting point, this S becomes closed. And this T also becomes closed because we are subtracting open sets from X. But here X is just, it is say disconnected. But for example, if it is disconnected but closed interval, look, from closed interval I am taking out open interval. It becomes not open, not closed, still not open set. You see, if X is open set, subtracting another open set is open set from the previous theorem. If you remember, if we take out, we have the set, open set, and taking out, this is the X. For example, this is the T. That if we take out, this is the set, our set. It is open, it is correct. But if X is open, then subtracting another open set is open set. But now, if X open set, then we are subtracting the from X, we are subtracting the open set, then it becomes closed sets. How we can understand? X is open set. So here I'm saying that X is an open set. Subtracting another open set will be closed. But if X is closed, then take out the some open set will be closed set. Okay, for example, if T, let's say 0, 2. I mean the X is this interval. And S 0, 1, 0, 1. And T is 1 to 2. Okay. Now, if I'm subtracting from X is, what does it mean? So I'm subtracting from all this interval from here. Okay. So it means this is 1, 2, 2 left. You see, it is not open, not closed. Not open, not closed. Why? S is open set. T is an open set. Okay. Now I am subtracting from X. This X is also open set. Open set minus open set actually becomes half closed set. Half closed. Because from 0 to 2, here 1, I am subtracting from 0 to 1 from all. From all. So what is 1 is not included. So if not included, this interval, including this 1, you see, including 1 to 2. Actually, this one not closed set. Open set. So it is not correct. You see, by example, I can see if this one open set, now we are subtracting another open set, resulting is not open set. Not open set. But if we have open set, union another open set is open set. That one we had the theorem. But for the subtraction, it's not correct. Now, when it can be, this one can be closed. Huh? When it can be closed. So if, look, if this one closed set, look, X is a closed set. And from closed set, I am subtracting the open set. So in that case, 0, from 0, I'm taking, sorry, here, X is big set. 0 is not included. 0 is not included. This is not correct. Whiteboard cannot see. I
don't want to know.
Okay. The computer. And please, this X also. Okay, I hope. Okay, are you hearing me? Usually, when we say like this, it is giving the close one. Not working. So in the case, it should be closed. Okay, now what's happening? If X is closed, I'm subtracting this. So 0 is not included. Here I have 0, union. So 1 and 2. You look, this is open closed set. Now, as I stated, closed set. To be closed set, X should be closed set. Then from closed set, if we take out the open set, you see here 0, 1 point, it is a isolate point, and at the same time, this is closed set. Closed set, union closed set is a closed set. You see, to be closed, X should be not only disconnected set, okay, minus 1, okay. Never mind that because it is a class time. So actually it should be like this, huh? So 0, 1, and 1, 2, 2. Okay, so this is the disconnected set, but you see this is half open. Now if I subtract S is the 0, 1, okay, 0, 1, and T, yeah, S and T. T is 1 to 2, two open sets. So I am subtracting from X 0, 1. 1 is not included. 1 is not included. Again, very strange. Because here also, because in order to be disconnected, we should take out at least 1 point. Once we take out 1 point, so means, so this is the disconnected set. From disconnected set, I'm subtracting the one open set. So 0 and 1, 2, 2. I'm subtracting 0, 1, 0, 1. 1 is included, but 1 because of this one not included. So from 1 to 2 and 0 here because here 0 is included. So this one is not closed set again. Is not closed set because 1 is not included there. So that's why I was surprised. This the proof of this theorem. You see, the proof says if S and T are non-empty disjoint closed. You see, disjoint closed set. Not open set actually. That S and T should be non-empty disjoint closed. No. This one non-empty disjoint open subset. S and T non-empty disjoint open subsets. So here open subsets. You see, correct. So it is said since X is X minus T and T is X minus S, both S and T are closed in X. Over there, they are open, disjoint open subsets of X. And from this formula, they say that this is a closed. Now I am constructing the example, not following this. Is it correct? My findings is correct. So this is the disjoint set. Look, X is disjoint set, but half open, half closed set. So now S and T is open set. So I'm considering X minus T. Okay, if I take like this, open, let's say this is open, and I'm taking out 1. So it is like this. What will happen now? So X minus S, what will happen? So I'm taking out 0, 1, 0 not included. Up to 1, I'm taking out all this. So what is left? So 1 is include 1 not included, 1 not included because it is not included in the set, and here 1 not included, and 2 is also not included, right? Is not included because of given set. 2 is not included, so this is the resulting interval. It is open, not closed. The empty set, and the R, there is a proof. Both of them are open and closed. Here they are stating there is not only the 0 and R, there are some sets which is open and at the same time closed. Look, here I'm having the open set, but this X minus S is not closed set. If I am taking this one as a closed set and taking out 1 point, then what will be happen here? Look, 0, I am not taking 0. 0 is included. 1 point is included. Union. Up to 1, I'm taking out. Now 1 is not in the set. So 1, 2, 2. I can say this is closed set, this is open set, also not related to the same problem. So that's why the proof of this theorem, I need to check. I try to find out similar theorem, proof of the similar theorem. Because over there, they say S and T are disjoint open set. But when S, this is correct. S actually, so since S, X is a union of SUT, so S is X minus T. It is correct. T is equal to X minus S. You see, if X is open, then subtracting another open set, it looks like closed set. It looks like closed set. But look, X is open. X is open. So X is open. Is open set. X is open set. And S and T is the open set. Now from open set, if I subtracting the open set, I am having this. 1 is not included. 1, 2, 2. You see, this one is open set. Is open set. It is correct. You see, open set minus open set is open set. If X is closed set, but still I disjoint. Actually, X should be disjoint. Disjoint, but including the endpoint 0, 2, subtracting 1. Subtracting 1, which is 0, 1, union 1, 2, 2. So X, the S equal to X minus T. Okay, what about this? Please pay attention. Actually, I am, this is actually T. This is T. Okay, now S, X minus T. X is this one. This is the X. This is the X. So, subtracting the T. T is from 1 to 2. If I'm taking out 1 to 2, 2 not included. So, it is 0 to 1, 1 not included, and number 2. Again, this one not closed. This one not closed set. To be closed set. Okay, this is the isolate point, and it is a closed set. This one should be closed set. Closed set plus closed set is a closed set. So you see that in the by example, I cannot conform. But theoretically, they say that this is a closed set. Okay, so please you also think about it. Now from the B to the C, I think it's okay because the B says if S and T are non-empty disjoint closed set in X with X equal to S plus T, okay, S union T, then the S is not empty and is not X, and also S is an open set in X. Open set in X, since S is X minus T. You see, X is a disjoint set. T is open, non-empty set. Okay, closed set. Closed set. Then S equal to X minus T is closed set. I think it is correct. That one is correct. So now please pay attention. X is a disjoint, non-empty disjoint closed set. Closed set. This one, non-empty closed set. X is non-empty closed set. B to C. So T are non-empty. S and T non-empty disjoint closed sets in X. So S and T is closed set. Now I am taking like this. Closed set. This is like this. Closed set. T cannot include the one. And X S union T. X union T. X is union S plus T. So actually here S and T non-empty disjoint closed sets in X. Closed sets in X. Closed sets in X. So I can say from 0 to 1, but this one, how can I take that as a closed set? S and T closed, it is a closed set, disjoint closed set. If I took like this is not disjoint. I mean, the intersection is 1. I cannot take like this. If I take open like this is not closed set. You see, 0, 1, 1, 2 is not closed set. So now from X, if I take out from X, if I take out S, I will have T. X minus S minus S. Actually, it is equal to T. Okay, let me see. X is this one. X is this one. So from X, I am taking out S. 0 up to 1. If I take out 1, then I will have 1, 2, 2. And this is really T. But T is not closed. It's not closed. So generally, this proof of this theorem is not very clear for me, you know, because S and T are the disjoint closed sets in X with X equal to S union T. You see? So it is closed, and the X is given as a union of two closed sets. Closed sets. If S is closed, T is closed, union is closed. So in the case, X must be closed set. So if I take write X like this is not closed set because one point is out. It is not closed set. You see, actually, if X is closed set means very strange point. See, imagine, according to the theorem, S is closed, T is closed, S union T is must be closed. If closed set, we cannot write it as a disconnected set. Disconnected set, because closed set includes interior point plus accumulation point. So there shouldn't be any gap. Usually for the disconnected set, we have gaps. At least 1 point, 2 points we have to take out from the set. Okay, so that's why the proof of this theorem is really not very proper, not very clear. Okay, let me check with some other sources. Maybe if it is clearly stated in other sources, then I will come back to this point. Okay, currently all these three, you see, from A to B is not clear. From the B to the C, again not clear. From the C to the A, let S be the open. Look, S be open and closed set in X. So look, S is not open, is not empty set. S is not R, but it is another new set which is open and at the same time closed set in X, such that X is not equal to S and is not empty. Okay, that one is okay. Since S is closed in X, X minus S is open. Okay, look, if S is closed set, X is also closed set minus closed set, or X is open set, S is a closed set. Then look, this is open set. I'm taking out the S, then it is open set. Then X minus S is open set in X. Since X is union of this, is the representative of X, so as a union of the non-empty disjoint open sets of X. But how to construct the S be open and closed set in X at the same time? Be open and closed set in X. Except two sets, I don't know any other sets which is closed at the same time open. Okay, that's why all these three are not clear. Okay, can you go next? So this theorem, the proof of the theorem is not proper, but as a formulation of the theorem is correct. Yeah, this one is now this one is not proper proof. Okay, the lemma, leave it and finish. I'm going to finish. Okay, lemma 3.2 says, let F be the non-empty bounded subset of R, and let A supremum of A, and B is the infimum of F. Then let epsilon is greater in the positive number, very small number. Then there exists in S from F such that A minus epsilon is less than or equal to S. There exists T such that the T less than B plus epsilon. This is the definition of the supremum. Okay, this one is correct. Now this one I will remove this theorem. I don't know what is wrong with this theorem. I can't clearly understand. So now next is that this lemma is okay. Lemma 3.3. The F be non-empty, close it. Let F be close it, be a non-empty. This is also important, non-empty. You see, it means non-empty, close it, non-empty, close it, subset of R. Okay, non-empty closed subset of R. Then if actually, sorry, non-empty bounded, not closed, bounded. The first one. This is the second one. Here, this is a bounded subset of R. Okay, subset of R. And let alpha is supremum. Alpha is supremum of F. Supremum of F. And beta is infimum of F. Of F. Okay? Of F. And epsilon is positive number. Then so the lemma says this is 3.2. The A, there exists S from F such that alpha minus epsilon is less than or equal to S. And for the B, there exists S, exists T, now another point from F, such that beta plus epsilon is greater than T. Is greater than T. This is infimum and supremum definition. Look, the geometrically, for example, strictly less, huh? Yeah, also strict. Okay. Good. Now look, this is the definition of the supremum. Actually, the B is called supremum of S. This S is actually, let's say, this interval. So B is called the supremum if we take any epsilon, very small epsilon, subtract from the B, then there exists S. You see, this S is less than B, but greater than B minus epsilon. So we can find point in F. So this the small subtraction of epsilon actually can lead to another point which is less than B but greater than B minus epsilon. So it means we cannot subtract anything from the B. That is a supremum. So now I think the proof is also very proper and correct because alpha is supremum, and suppose that alpha not belong to the F, because supremum sum can belong to the F, may not belong to the F. If it belongs to the F, then it becomes maximum as well, because for the maximum, the alpha is included. So that's why we should consider alpha not equal to B. By lemma 3.2, yeah, sorry, I'm going to the down again. By definition, alpha is the upper bound of F. Yes, because the supremum of F means alpha is the upper bound. If upper bound of F and belong to the R, suppose that S, now you see, here in the proof, suppose that the S is less than alpha minus epsilon. See, actually here I'm stating that S should be greater than alpha minus epsilon. Here we are supposing that because this is contrapositive proof we are using. So that S, you see, alpha is a supremum. This, yeah, because here it's strict, so here we can say can reach. Yes, it is correct. Here strict, and when we suppose the opposite one means can reach. Okay, alpha minus epsilon. and alpha is supremum, therefore it is the upper bound. And from the upper bound, we are taking out some epsilon. Okay, so S now less than alpha minus epsilon. It is correct. And but S from F, from F. It is the element of F. Element of F. Then alpha minus epsilon is also upper bound of F. So if we suppose like this, then alpha minus epsilon is also upper bound bound of F. You see, alpha is upper bound. Alpha minus S is also upper bound. So we have two upper bounds. Okay. Next, upper bound of this one contradicting the fact alpha is the least upper bound of F. Now, how can I confirm that statement? Alpha minus S, you see, alpha is upper bound. What is the definition of upper bound? So every element of S, should be less than alpha. Should be less than alpha. That alpha is called upper bound. Now, S is also less than alpha minus epsilon. I am taking out some epsilon. Still, it is the upper bound. No, this one cannot be upper bound because of definition. Definition says if alpha is upper bound, alpha plus epsilon can be upper bound, not less. Okay, subtracting some point cannot be upper bound. So it means this contradiction brings to the truth. You know, if alpha is the upper bound, alpha mu minus epsilon cannot be upper bound. Okay, so alpha minus epsilon cannot be upper bound according to the definition of upper bound definition. So that's why I think this one is okay, correct. The second one, I hope you can use the same type of similar proof. By using the similar proof, you can prove the second one for the lower bound. For the lower bound, you know, you should say opposite. This alpha beta plus, you see, beta plus epsilon is also lower bound. You suppose beta plus epsilon is also lower bound. Then at the end, come up with the contradiction. Okay. So, okay, this lemma is okay. Next lemma is also okay. Let F be the non-empty closed subset of R. If F is bounded above, then supremum F belong to the F. If F is bounded below, then infimum of F is, because here, you know, F is closed. If F is closed, then the supremum of F is also element of F. Is also element of F because of closeness. Okay. Lower bound, the infimum of F is also element of F because of closeness. Okay. I hope that proof is very clear and given proper. So just example 3 and we finish. Okay, almost this one we are going to finish already 10 o'clock. Let X minus 1 1 is connected. Okay, now example, this example we try to prove properly. Huh? Okay. F is closed. So alpha is supremum of F, is the element of F. Beta is infimum. Infimum of F is also element of F. So actually there is that proof you can see. If F is closed, then supremum and infimum also included in the set. It is correct. Actually, that one is leads to the maximum and minimum. Okay, maximum and minimum must be in the set. Okay, I hope that this one I will remove. Just one example I will explain and finish this chapter fully. You see, even it looks like simple, this connected and disconnected set, but has many contradiction, not very easy to understand. There are such kind of points. Okay, now this one is coming in. So the X is connected set. Now let example 3. Let X is connected set. For example, say choose minus 1, 1. Minus 1, 1 is connected set. Connected set. Okay, connected set. It's connected. The set actually they are going to prove that this set is connected set. Okay. If we are not taking out any points from the interval, then it is a connected set. So the actually this is looks like statement. Actually, this interval is connected set. To see this, let F be the closed subset of X such that F non-empty but not equal to X. So we will show that F cannot be open in X. F cannot be open in X. So they want to show that F is the closed subset of R. Now F the closed subset of R or closed subset of X. Okay, closed subset of X. Okay, and non-empty. Non-empty is not empty. Is not empty. And not equal to X also. Not equal to X. It is not fully covering the X. So then F cannot be open set in X. They try to show F cannot be open set in X. It must be closed set. So if it is a closed set, every subset is a closed set, then this set is not disconnected. Is not disconnected. They are trying to show that there is no. You see, every subset of X is closed set. They are trying to show. If every subset is closed set, then given set cannot be disconnected. So they are trying to show that one. So to do this, what they say, they take the X and Y from different. So X, they take from capital F, and Y, they take from X minus F. X minus F. So it means we have minus 1, 1. Okay, this is our interval. And X lies, that F, this is capital X. Let's say this part is F. So X lies in here, Y lies in here. X minus F means here. So X lies here, Y lies here. So 2 points, we are taking 2 points from the set. And X less than Y is correct. So X is less than Y. Also correct. Okay, so if it is so next is what? Letting Z supremum of F T less than Y. Okay, Z, we are taking supremum of all the T from F. You see, F is a subset such that T less than Y. T less than Y. So they are taking like, looks like this. So it lies here, T also lies here, where it is a variable, all the F, T less than Y, and it is a supremum. So supremum means, here, this is the Z. Z is here. So it can reach up to the Z. So Z is a supremum of T from F then T less than strictly less than Y. Okay, it is correct. So we have now this X is less than T, right? Is less than Z, is less than Z, and this is less than Y. It is correct. So X varies here. Z is a supremum of F, so it is greater than X, but it should be less than Y because it is the supremum of this set. So this one is correct. By lemma 333 Z from F. By lemma 3 Z belong to F. So from here Z belong to F. It is supremum. Previous theorem, if F is closed, then supremum is in the set. In the previous theorem, we have proved. Because this one, the F is closed set. So that's why this supremum also belongs to the F. It is correct. So Z belong. But Y not belong F and Z strictly less than Y. Over there, they say that can reach to the Y. But here, Z strictly less than Y. Okay, since Y not belong to actually it is correct. Since Y not belong to the F, Z should be strictly less than. It is correct. But here also correct. This is general statement. Now, since Y is not F, so Z should be strictly less than Y. It is correct. By the definition of the supremum, ZY intersection with the F is equal to what? Is equal to empty set. Is equal to empty set. Why? So ZY intersection with the F is empty set. It is empty set. Is it correct? So Z Y is here. A very small one is also very close to Z, but it is Y cannot take the Z. So we have the small interval intersection with the F intersection, but this one is the open interval, correct? There is no intersection with the F is empty. Because F is this part. ZY is this part. This is Z and Y is this interval. So intersection with the F is empty, correct? It is empty. Then, therefore, the no open interval is contained in the F. No open interval. So Z minus epsilon, Z plus epsilon, no open interval. Z minus epsilon, Z plus epsilon is contained in F. No such kind of. Why? Only this one we need to understand that is contained in F for all epsilon. So F is not open in X. F is not open in X. So if Z is a supremum of F, so this interval is not belong to F. Is contained in F. Is contained in F. Is contained in F. Why? Therefore, no open interval is contained. Means it is correct. No open interval is contained in F. No, because over there, no open interval is contained in F. So, because Z is a boundary point for F, therefore this one cannot be completely belong to the F. So, it means the F is open, is not open. So F is not open in X. No open interval is contained in F for any epsilon greater than 0. So F is not open in X. And the epsilon very small, epsilon positive number for any positive epsilon. Here, you know, f is not open in X. If y is less than X, a similar argument can be used and show that S cannot be open in F. Here, F is not open in X. F is not open in X. Okay, F is not open in X. It's not open in X. If F is not open in X, is not open in X, so then X is closed and it cannot be divided into two. So you see, this one, you know, this one shows that Z minus epsilon, this interval, is this interval. It shows that Z is not interior point. If Z is not interior point of F, is not interior point of F, here we say that is the interior is it belong to the F, and but here it is not interior point. It is belong to the F, correct, but not interior point. If Z is not interior point, so F is not closed set. It's not closed set. So that F is not open means closed set. X is contained. This is not contained. No open interval is contained in F. So F not open in X. So F is closed. Is closed in X. F is closed in X. It means F is closed in X. Okay. Okay. I hope it. Look, point Z is a supremum of F, and did not belong to. It is belong to the F. Z belong to the F, but it is not interior point of F. Please pay attention. Z belong to the F, but not interior point. So if it is not interior point, it can be boundary point or accumulation point. If it is a boundary point included to the X, then if supremum is included in the set, then F is closed set. Yes, then this one not open, so F is closed. Is closed means that one. It is closed. Is not can be F is not open in X means it is closed. So if it is closed set, then this Z moves to the end, because if I can construct such a way that it is a subset of X, but this Z can be moved up to the end. So F is closed, and this Z is included in the set. It means it is a maximum point as well. So this set is closed set. Okay. So if it is closed set, it cannot separate point. It is connected set. It is connected. So that's why at the end they say if S is connected subset of R, then S is interval. Okay, S is interval. If it is connected set in R, then it is must be interval. Okay, now look, if I take X S 2 points, for example, -1, 0, 1, what we can say? Is this connected set or disconnected set? Hello. How do you think? Now I am taking just 3 points from this interval. -1, 0, 1. 3 points I took. Is this set connected or disconnected? Connected or disconnected? How do you think? According to the last the theorem, if S is connected, it must be interval. You can see it is not interval, so it is automatically disconnected set. If it is disconnected set, how we construct U and V? U and V. How we construct U and V such that the X should be written X the first U intersection X union V intersection X. So I should choose U and V such a way that they are U and V intersect. It is disjoint. It should be disjoint, but X equal to like this. Okay? You see, generally it is not very simple to show. It is disconnected set. It is correct. But for this case, how to construct U and V? Or I can say U, V, W. Maybe here I can say another W intersection X. You see, I can construct three subsets of X such that X can be given like this. Okay. Now look, U -1 plus epsilon. I'm taking 1 point. 1 point plus epsilon. V minus epsilon plus epsilon. And W is 1 plus epsilon. Is it okay? So I'm constructing three. They are disconnected. U intersection V intersection W are empty set. And intersection U with X non-empty, intersection V non-empty, intersection. Now, can I say that important thing? What about U intersection X? Okay, and if U intersection X gives -1, then it is okay. Can I say U with X? You see, -1 not included. U is not included. X is included. So here, I should say -1 plus epsilon. I'm taking interval now. You see, if I take 1 plus epsilon -1 plus epsilon, then I cannot get X. Now, this one gives -1. You see, this interval with X intersection gives this. V intersection with X gives 0, 1 point. W intersection with X gives 1 point only. So the union gives X. So I was able to construct not 2, because depending on the problems, we can find 2, 3, 4, 5, and n. Okay, so that's why please pay attention. So if it is not interval, then it is disconnected set. Okay, particularly this one is a disconnected set. This one is also disconnected set. X equal 0, 1 minus 1 point, for example, 0.5. If I take out 1 point, if I take out 2 points, 0.9, if I take out 0.95, you see, 3 points I'm taking out from the set. Of course, it is a disconnected. So U, V, W, I have to construct 3, not 2. Okay, I need to construct 3 with disjoint open sets or disjoint closed sets, such that X should be equal to union of 3 sets. Okay, that's the disconnectivity of the sets. Okay, now just 5 minutes rest. Then we continue our next. Okay. Next lecture. Yes. What time is it? Why? Oh, 10:50. In that case, please open. We don't have a break. So too much I stop on this. And why you 2 hours just almost we are finishing, but because of that the 2 points took the time. The proof is not proper. So there is one more, the new one. Open the new one. Yes. Bring down that one. Bring down. Total. You bring all down, or okay. In this case, stop sharing. Stop sharing. So go to the yes and open the next. Okay. So now you again sharing. 10 minutes left only. Yeah. This is too much. Too much. I wanted to show your results also. I mean the solution of the midterm test. Now no time at all. Okay, I hope connected, disconnected set is very clear now. Huh? So now the new actually this week is week 11 or week 10? Please they increase the size. Hello. Sequence. Sequence. Sequence convergent. Convergent. Convergent sequence. Okay, thank you. So now please pay attention to definition 1. A sequence is a function whose domain is n. A real sequence is a sequence whose range is in R. Okay, now definition is very interesting and very simple. Definition 1. A sequence is a function. Huh? Is a function. Is a function. Actually, sequence is a function. You see, definition is very nice. Is a function whose domain is n. Whose domain is n. Usually, domain of in the normal case, domain is R. But here they say domain is n. Okay, is n. Then another one, a real sequence. Yeah, real sequence. Real sequence. Real sequence is what? Is a sequence. Is a sequence. Is a sequence whose range is R. Now imagine. Just I'm taking one sequence. Actually, usually the sequence we denote by A sub n, B sub n, C sub n, and so on. But I can denote it with function f of n. Now you can see from here n 1, 1, 2, 3, and so on. So it is really the domain is N. It might be Z also, but of course 0 is not included here. So what about range? Range is R. Huh? When N equal to 1, it is 1. So this is a point. N equal to is half. N equal to 1/3, 1/4, and 1n. If I draw the graph, of course I cannot draw the graph. Why? Because we don't have value here. We don't have value here. But as an imagination, this is a function with the dot points. You see the just points, discrete points. It is a just discrete points. You can see it is a just discrete points. You see the function value is 1, 1/2, 1/3, 1/4, 1/6, and so on. Okay. So now another word, you know from the calculus, if I take the limit, then the limit of 1/n, as n tends to infinity, so it tends to 0, right? It tends to 0. So it means it never reaches the 0. It tends to 0. As the limit value, we can consider 0 is a limit of this sequence, and it is a convergent sequence. Okay, if I take just alpha n as n over n minus 1, okay, and as this is the f of n, also I can consider is a function whose value, of course, here please pay attention, n belong to the n, but not 1. 1 is excluded. Okay. In that case, if I draw the graph of this function, what will happen? So this 1 is not included. 2, 3, 4, and so on. And look, what then the points? When n equal to 2, 2/1 is 2. 1, 2. So I have at point 2, I have this point. N equal to 3. 3/2. You see, 3/2. 3/2 is less than this. 3/2, the half actually, is half of this. So I have this point. Next, I have this point. And so on, I have this point. But please pay attention. It never and ever go down beyond this line, y equal to 1. Okay, so you see, it approaches to this point, to this line, but never cross. So that's why limit of alpha n as n tends to infinity, so n over n minus 1 as n tends to infinity tends to 1. So 1 is the limit of this sequence. So we are talking about the convergent sequence. Just now we have seen the two sequences are convergent. Okay. Now what does it mean convergent? So we need to give proper definition and proper scheme. Convergent, divergent, bounded, unbounded. The many things we will learn tomorrow. So actually, I wanted to finish one part of this chapter. So just started. SubhanAllah, so much time. Okay. Anyways, that's all. If you imagine the problem well enough for today. Thank you very much. Please Yes, 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 please. Thank you. Ah, this is real analysis. Headache. Think, how come this theorem is not proper? Because example shows it is not correct, but it should be correct. Okay, so this.
Tomorrow, you doctor.
Actually, we have the big celebration, huh? Day of tomorrow. Day, huh? A container. Bring your own. So they don't have. I also didn't bring. So where is the place? Number of chances. So okay, I can open.